Hello, I'm Veena Marlena, and welcome to Open Access Tools for Physical Sciences, a series by Physical Sciences Consultorium, where we explore powerful open access software that is transforming modern scientific research. In today's episode, we'll discover ORCA, one of the world's leading quantum chemistry packages, and understand how density functional theory, or DFT, helps scientists explore the fascinating world of molecules. Let's begin. Everything around us is built from molecules. The medicines that improve our health, the batteries that power electric vehicles, the displays on our smartphones, and the materials used in solar panels all derive their unique properties from the arrangement of atoms and the behavior of electrons within molecules. To create better technologies, scientists must first understand matter at the molecular level. And that's where the real challenge begins. At first glance, a molecule appears to be nothing more than a collection of atoms bonded together. But its true behavior is governed by something much more fundamental: its electrons. Electrons determine how atoms bond, how molecules react, how materials conduct electricity, and even how they interact with light. However, electrons do not behave like tiny planets orbiting a nucleus. Their motion is governed by the laws of quantum mechanics, making the microscopic world both fascinating and incredibly complex. Traditionally, scientists have relied on experiments to understand the properties of molecules and materials. While experiments remain essential, they often require significant time, resources, and careful preparation. But what if we could predict the behavior of a molecule before it is ever created in the laboratory? Today, computational chemistry works hand in hand with experimental research, allowing scientists to simulate molecular systems, test hypotheses, and guide experiments with greater confidence and efficiency. Modern computers have transformed the way scientific research is conducted. Today, researchers can build virtual models of molecules, simulate their behavior, and investigate their properties without stepping into a laboratory. These computational experiments help scientists understand molecular structures, predict physical and chemical properties, and even identify promising materials before they are synthesized. In many areas of research, the computer has become an indispensable laboratory for scientific discovery. If computers are so powerful, why can't they calculate the behavior of every molecule exactly? The answer lies in the electrons. Every electron interacts with every other electron through electrostatic forces. As the number of electrons increases, the complexity of these interactions grows dramatically. For even moderately sized molecules, solving the complete quantum mechanical equations exactly becomes practically impossible with today's computing resources. This challenge is known as the many-electron problem, and it has been one of the greatest obstacles in computational chemistry. Instead of following the motion of every individual electron, scientists asked a different question: what if we study the overall distribution of electrons instead? This simple yet powerful idea forms the foundation of density functional theory, commonly known as DFT. By describing a molecule in terms of its electron density rather than the behavior of each electron separately, DFT makes accurate quantum mechanical calculations practical for a wide range of molecules and materials. Today, it is one of the most widely used methods in computational chemistry and materials science. ORCA is one of the world's leading open-access quantum chemistry software packages. Developed by Professor Frank Nice and his collaborators, it provides researchers with a powerful platform to perform electronic structure calculations using methods such as density functional theory and many others. Today, ORCA is used by universities, research laboratories, and industries across the globe to investigate the properties of molecules and materials. Its accuracy, versatility, and open access nature have made it an indispensable tool for modern computational research. ORCA is much more than a calculation engine; it is a powerful toolkit for exploring the molecular world. Researchers use ORCA to determine the most stable molecular structures, visualize electron density and molecular orbitals, predict infrared and UV visible spectra, investigate magnetic properties, analyze non-covalent interactions, and even study the pathways of chemical reactions. By revealing these microscopic details, ORCA helps scientists understand why molecules behave the way they do and supports discoveries across chemistry, physics, materials science, and related disciplines. Today, ORCA is making a significant impact across many areas of scientific research. It helps researchers design new drug molecules, develop efficient catalysts, improve battery and solar cell materials, investigate nanostructures, and understand the optical and electronic properties of advanced materials. Whether the goal is cleaner energy, better healthcare, or next-generation technologies, ORCA provides valuable insights that guide innovation and accelerate scientific discovery. Scientific progress thrives when knowledge is shared. For many years, advanced computational chemistry software was accessible only to institutions with substantial resources. Today, open-access tools like ORCA are changing that landscape. Students, educators, and researchers across the world can now access state-of-the-art computational methods, learn modern electronic structure theory, and contribute to cutting-edge research, regardless of where they work. Open science is not just about free software, it's about making scientific discovery more inclusive, collaborative, and accessible to everyone. ORCA has shown us how quantum mechanics, computational chemistry, and open science come together to help researchers explore the invisible world of molecules. But this is only the beginning. Many other powerful open-access tools are enabling scientists to model, visualize, simulate, and analyze the physical world in remarkable ways. In our next episode, we'll explore Avogadro, a versatile molecular editor that helps researchers build and visualize molecular structures before computational calculations begin. Thank you for watching. If you enjoyed this episode, please like, share, and subscribe to Physical Sciences Consultorium. Until next time, keep exploring, keep learning, and keep advancing science.